So I don't know too much about radio, GNU Radio, so that was the first time I heard about it, to be very honest. So I hope at least I can give you somehow a perspective on, I'm a researcher at FAIR, and I'm a researcher at GSI. I came actually from the Netherlands 3 years ago. I was there for 25 years or so, an associate professor. And I moved here because of essentially this particular facility, because I like it so much. This is the future also, hopefully for me, before the retirement, I hopefully also will be able to see this beautiful facility being ready and enabled to run physics with these FAIR accelerators, right? And the reason why I was so enthusiastic to move to GSI and FAIR, well, first of all, I was already connected to GSI and FAIR, but somehow I had to stop my research in the Netherlands, is because I like the facility because it has a lot of research topics which it addresses, from atomic physics, material science, biophysics, particle physics, nuclear physics, hadron physics, this is what I'm doing by the way, heavy ion physics. So there's a very broad community with a lot of physicists on an international level, connecting also to other research facilities like for instance CERN or a J-Park or a J-Lab in the US and Japan, which makes it very exciting to do research here, right? And the nice feature of FAIR is this high intensity, being able to do precision, do forefront kind of physics. And I will hopefully also give you somehow a flavor of that. But I will also connect it to technology, in particular to software development. And hopefully I also somehow resonate with you guys and see how that works out, right? Okay, but I have to make a confession. I already said it. My background, I'm a physicist. I'm not a software engineer, although I'm actually the FAIR computing coordinator for the FAIR experiments. So in that sense, it's more or less a self-educated, if you want, software engineer, right? If any. I mean, I'm already now, 53 years old, so I think already the younger generation knows much more about things than I do. But nevertheless, my background is physics, I'm not an engineer. So that's one thing. The other confession that I make, GNU Radio, I only learned about it very recently when Ralph actually invited me to give here a talk, right? So I was also thinking, so GNU Radio is something interesting. So I asked my colleagues in the same experiment where I work at, and they say, yeah, no, we don't know what GNU Radio is. So I ask, of course, the holy grail of anything is, of course, ChatGPT to help me out here, right? So I asked her, how can I use GNU Radio 4.0, that seems to be the new version, doing hadron physics, but that's what I do, I will explain later on what it is. How can we connect, right? That's basically what I ask. And of course, ChatGPT is always very positive, so it starts with very positive statements about what it knows about GNU Radio, what it knows about hadron physics, what are the topics over there. Now, yeah, this particular text I could also think of how to write there, but then it really became extremely creative. Extremely creative. Let me show you here. So it came with suggestions. Point 1. Yeah, maybe do something with signal processing from detectors. Yeah, of course, that's an item which I'm also dealing with, right? All kinds of suggestions. Another one here, real-time data acquisition and monitoring. Yeah, this is certainly something common between us in a certain way. Timing, synchronization, absolutely. Data analysis on a higher level now, data analysis, event reconstruction. Yeah, that is also the big business, what you're doing in a hadron physicist experiment. Simulation, prototyping. Yeah, we have to prepare the experiment, we have to do simulation, so maybe we can connect there. Or doing network data collection, or training. So it came with all kinds of suggestions. If you read them, yeah, they somehow make sense. I mean, then I also start wondering, wow, maybe somebody wake me up. Maybe I'm missing here something. Maybe there is something which we can somehow share with each other, right? That's the first thing I learned from this particular exercise. The other thing is, who says that AI cannot be creative? I will come to this particular point also later on again, because I do think that AI is really becoming something interesting. But okay, later I will talk about that later. Okay, this talk, the objectives, a couple of them. I will talk about science and technology at GSI FAIR, the why, the how, the what. I will not discuss the whole FAIR experiments and research activities, but I focus very much on what I personally do. Right, so that is, I think I also feel a little bit more comfortable talking about this. I will talk also a little bit historically, from the past, the present, and the future. It becomes a little bit like a roller coaster in a certain sense, but I think there is a certain thread in my particular talk, right? So be aware, this is what I'm trying to somehow convey to you. And hopefully we come back to this JetGPT kind of question and see how we can actually, communicate with each other. Okay, few words on the why. I'm a Hadron physicist. A Hadron physicist is a physicist who's looking essentially at on the elementary level, on the femtoscale level, to particles. So here we have an atom. Let me try to find the pointer here. So here we have an atom, right, and then we have the atomic nucleus, nuclear physics, and I'm interested to look at the building blocks of an atomic nucleus. These are the protons and the neutrons. So that's, for instance, an example of a typical hadron. But there are many hadrons. Now, hadron has a meaning. Hadron means massive, bulky, lumpy, or whatever. That's essentially the Greek name of hadrons, in contrary to leptons, which is small and tiny. So you might wonder, so what is now so massive about a hadron? So let's just look at a proton, some numbers of a proton or a neutron if you want. Let's look at some scales here, right? Okay, a proton has a mass about 10 to the minus 27 kilograms. Well, that's not very massive. We like to always put in a different units. E is mc squared, so the mass is the energy divided by the light velocity squared. So we say 940 mega electron volt over c squared, so about 1 giga electron volt. That's the typical mass. This is small, right? So that's not very massive. The size of a proton is in the order of 1 femtometer. So this is why we call femtoscale research. It's my title of my talk, right? So that's in the order of 10 to the minus 15 meters, right? Also not very massive, I would think so. But if you now look at the mass density, how much mass per unit volume a proton contains, this is actually impressive. It's 10 to the, you can calculate it yourself, not so complicated, right? Assume that it's a sphere, right? 10 to the 18 kilograms per cubic meter. That's the mass density of a typical hadron, the proton or the neutron. It's a huge number, right? Just to compare the density of the Earth, 10 to the 3, 10 to the 4. Yeah, and if you really want to go on an astronomy level, yeah, a neutron star, for instance, they're getting close to it, 10 to the 17, right? But you really have to go to extreme objects in the universe to find something equivalent to a mass density of a hadron, right? So by studying hadrons, you study mass. That's the whole thing of what we're trying to do in hadron. This is the why, right? Okay, you might think, but we know what a proton is. Wasn't that these quarks, right? There were, these up and down quarks, elementary particle standard model. You put 3 together and you have a proton, right? Well, I will disappoint you here again, because look at the proton mass now again, right? The quark mass, we know that's the Higgs mechanism. That's what they figured out. There's certain, for instance, right? A quark has a mass of the order of a couple of mega electron volt. 3 of them give you in the order of 10 mega electron volt. A proton is like 1,000 mega electron volt. So only 1% of the proton mass comes from the Higgs mechanism. Right? So understanding the mass is apparently this is not that simple, that picture. This is more like this. There's all kinds of dynamics going on. Some funny dynamics going on which create mass. This is, of course, something that has to do with the interactions of these quarks. It has to do with the force carries of the quarks. For whatever reason, it generates energy. And this is something which we try to understand. The origin of mass. We really do it here, right? So that's the reality. Okay, so and that all has to do with a theme which is called the strong interaction. The strong interaction, the interaction between what we call color charges. That is essentially where the key is, what we're trying to understand. Now there is an equation around it. I mean, you see on my t-shirt there's also this funny kind of equation. This is the wrong one. This is the Higgs mechanism. We don't like that. We like that equation. That's quantum chromodynamics. That's describing, if you want, the equations of motion in some particular way of color degrees of freedom, quarks, right? Now, like radio waves, you have electric charge, you wiggle electric charge, you get radio waves. If you wiggle a color charge, you get gluons, gluon waves, right? This is what we are studying, gluon waves, right? And this has a certain particular interesting dynamics which we don't yet understand. We know the formula of this. You cannot calculate it, from first principle. It's very complicated. And even if you would be able to do it, and there's a lot of people trying to do it, it still is a question of what is really behind it? What is really the mechanism which creates then the masses of these particular hadrons? What is the original mass? What are the properties of hadrons? How are they actually being formed? What are the underlying symmetries? This is the questions which we're trying to understand, and this is also where FAIR is contributing. These are the 3, if you want, big collaborations one is now left out, that's the atomic physics here, which are trying to address this quantum chromodynamics. And that's already a theory which is 50 years old. More or less when I was born, this theory came about. That's the standard model. The interactions of quarks, these are the quarks here, this is the standard model, up, down, and that is what the protons and neutrons are made out of, right? But you also have heavier quark charm and strength, which we can do with FAIR. And we can try to see how hadrons are being formed out of the quark by these gluon kind of mechanism, right? Okay, so that's the thing. Now, how do you do this? How do you start? Well, first of all, you have to come with a collaboration, right? And the collaboration, what we're talking about, is in the order of about 500, 400 people or so. This is actually the picture of the Panda collaboration, already from quite some time ago. And the way to do it, let me just conceptually give you an idea how you study these particular hadron mechanisms at FAIR. Well, you start with ordinary matter, and I put the analog like a house. You want to understand what is making a house as it is. What makes a house stable, for instance, right? What are the properties of a house, right? So what do you do in order to understand the details of a house? Ordinary matter, a proton, for instance, ordinary matter in our case, right? Well, what you can do, for instance, is try to stretch it. Try to see when it starts breaking down, put different bricks in there, different colors, and see when it reaches its end of stability. This is what you do here. For instance, if you go to Darmstadt, you have these kind of funny buildings there, right? I mean, or you go to the Netherlands, you have also these exotic buildings at the University of Groningen. Where is the limit of stability? And you hope by going to extremes, to extreme matter, to learn something about the ordinary matter, right? You try to stretch it to a limit, and by hoping to see where it starts breaking it down, or what the properties are of these kind of things, you hope to learn something about the underlying matter. That is essentially, conceptually, what we do at FAIR. Now, in hadron physics, you might also know, of course, we have ordinary matter. So these are the house, if you want, the protons, the baryons, and the mesons. These are called the protons, for instance, the neutrons. There are also particles which are made out of quark and antiquark. That's called the mesons, pion, for instance. These are ordinary matter. But if you ask somebody who knows about quantum chromodynamics, they also, yeah, but in principle you can also form exotic matter. You can also have matter made out of 4 quarks or 5 quarks. You can also have matter which is made out of these gluons, these waves, these strong interaction waves, if you want, creating a certain massive particle without any quarks. All these things in principle is there, but we have to look for it. This is what, for instance, this Panda experiment is trying to do. Also, my friends from the heavy ion physics, you already saw yesterday these pictures of these heavy ion, particles accelerated, and they bang on other heavy ion, and they create all kinds of very dense matter with all kinds of different particles. Well, their aim is try to understand the so-called phase diagram of quantum chromodynamics. Like you have for water, you have different phases, a solid phase, a liquid phase, a gas phase. Also in this QCD matter, we expect to see these kind of phases. And of course, one of the things which we like to do at FAIR is to look at very dense matter. So be somehow related to, for instance, the properties of a neutron star. Another form of creating exotic matter. And if you talk to my friends of nuclear physics, well, they also look at extremes of nuclear matter, right? This is a nuclear chart. You've also seen it yesterday. And the extreme thing is trying to look at nuclei where you have many, many neutrons in there and see when they are starting to be unstable. And looking at these particular properties. This is, again, the same kind of philosophy. And the other thing is, for instance, which was not said yesterday, is that we also like to look at nucleons, so nuclei, where you have protons and neutrons, but instead of having a proton and neutron, you put another hadron in there, another baryon, which have strangeness in there, a strange quark. These are called hypernuclei. This is also a dimension which goes in this direction. So extending the nuclear chart to even going to very extreme kind of particles, right? So this is the philosophy what we are trying to do here at FAIR, looking at exotic matter to learn something about the underlying thing. Now we have facilities for that, right? This is FAIR, this is, of course, you have seen it before, this is GSI, this is how FAIR should look like, right? The CIS 100 ring, and then all kinds of caves and experimental facility. Now if you look at hadron physics, this is now my interest, there are a couple of experiments being planned, hopefully in the future. The so-called Panda experiment, which uses antiproton, which are stored in a ring, hitting a proton target, coming from a pellet target or whatever, with a detector around it. This is a typical high-energy kind of detector, this onion shell kind of detector. You collide antiprotons and protons, you generate, for instance, this weird matter. You look at their decay, and the decay products you measure with a whole set of detectors and with a variety of detectors with many kind of sensors, and each sensor has its own kind of capability to detect a particular type of particle, their energy, their momentum, and so on and so forth, right? So you see these kind of complex kind of detectors. Now another one is, for instance, the CBM detector, the compressed baryonic matter detector, used primarily for heavy ion reactions, but also here one can do hadron physics as well. It's a different type of detector. It's not in the storage ring. You come with heavy ion or proton beams and you hit their particular target, and you're looking at also here some kind of modular kind of detector, but in principle a very similar kind of concept. Now this is the future. We also have an experiment which I guess this afternoon you will see that setup. It's called the Hadron detector. This is primarily designed for precision dilepton spectroscopy, if you want. It has a beautiful magnetic field, being able to identify and reconstruct E plus, E minus pairs, but it also does many more. There's the hardest experiment which we are using today to do these kind of experiments. And then, of course, we also have another important thing, which is a green IT cube. We also have our own HPC center, which is again something very important. One always forgets about it, one thinks about these detectors, but this will become over the years more and more important. Why? Because we are producing more and more data over the years with higher and higher rates. Just to give you some feeling, once FAIR is running, we will produce, this will store in the order of 35 petabytes per year. We'll have about 300,000 cores. 100,000 cores will be also distributed in other facilities. In the order of 500 GPUs. So this is really a big facility which is supporting the data flow, the data analysis of these kind of large experiments, right? So this is the facility. This is what we are working on. Okay, let me give you some illustrative case, right? So some example. So we're also now getting closer to, you know, what kind of challenges we have. Well, there are particles which have been discovered, for instance at CERN, or in China, and E plus E minus colliders, which are weird. They're extremely weird. They also have a name. They call it the XYZ hadrons. They don't know what it is, so that's why they call it XYZ, right? But that was about a decade ago. There were, maybe you saw it also in the news. This is, I think, in the order of 10 years ago, 2013 to 2015. There were many of these kind of particles detected at all kinds of facilities in the world. The XYZ discoveries, right? Now we believe, or we hope, that these particles are these well-known or well-expected exotic particles made out of 4 quarks or made out of 5 quarks, called the tetraquarks and the pentaquarks, but we don't know it yet. There is no ambiguity. There are a lot of questions whether the things that we observe in these experiments are really somehow pointing out to these kind of particular states. So how do you figure out? Well, what you have to do is actually try to measure their composition. To measure, do precision studies, measure their masses very precisely. This is one of the keys. Measure the mass uncertainty, their lifetime very precisely, which you then use in order to really confirm or deny, if you want, that these are the particles which people are looking for, right? This is something which we like to do in Panda. Okay, so how do you do that? Well, you need precision, and this is exactly what we do at FAIR. We have precision experiments. Precision means 2 things. Once you design an experiment which have an excellent kind of resolution, think about mass resolution, and on the other hand also produces abundantly statistics. If you don't see anything, of course, also it's useless, right? Okay, so how do you do that in this particular example? Well, mass measurements is an important theme also at FAIR. And with the storage rings, we have storage rings, we'll be able to get mass resolution in the order of 10 to the minus 5. So you can do a very precise mass measurements of, for instance, this XYZ state, right? Statistics, well, that means you have to design a detector which can cope with huge rates. Why? Because these states here, what we're looking at, they have a very small probability of being created. We express it in terms of cross-sections. If you are known it must have a sensitivity of less than a nanobar. So you mean high beam intensities and the detector capability with high efficiencies, high acceptance, and so on and so forth, right? So this is something which essentially one is trying to focus on. Now, this is the HESR ring, the high energy storage ring. This is meant to collect antiprotons. So this is a picture of the whole setup here. Of course, this is still future. We're talking about 2030 something, right? This is the Panda detector, so the antiprotons are injected here, and they are cooled. They are cool. We already had yesterday about this concept of stochastic cooling, and this stochastic cooling is the key in these kind of things. And this is also why we like these kind of storage rings, because it allows us to actually have a very well-defined momentum of the antiprotons. This is a key, right? And that is by stochastic cooling. Yesterday it was already explained nicely, and it was also said it has actually a Dutch contribution. Simon van der Meer got a Nobel Prize for this kind of invention, right? And that gave to the rise to the discovery of the weak charge particle, the weak force carries, the W's and Z at CERN, right? So that is together with Rubia. So this is really a key element, something which was already known in the 80s as techniques, but now we're really going to use it to do precision mass measurements by using this precision momentum of the antiprotons, right? So this is the reaction. You hit an antiproton, well-known momentum on the proton target, no momentum. You create whatever exotic objects and you look at the decay products, right? And what you can do, for instance, if you roughly know where the mass of this particle is, you can do a scanning with a very precise beam, with a very low, with a very good resolution. You can scan, and at some point you hope to see a particular peak. In this peak position and also the width you can use to determine the properties of these particular exotic states, right? That's precision. This is one thing. The other thing is statistics. And now we come to problems. Now we come to data problems, if you want. Now the statistics, the problem is that the probability of creating these exotic particles is very small. This shows you essentially the probability, we phrase it in cross sections, of proton-antiproton reactions. Most of the proton-antiproton reactions generate something completely garbage we don't really care about. This is essentially sitting there. This is how these are just some elastic or some particular processes. And 1 out of the 10 million kind of events we expect to produce these kind of particles. Right? So this is a challenge. So we have to somehow, first of all, we want to generate many of these things. Right? That means we need a high intensity beam, right? And then we also have to be able to suppress the background. We get a lot of garbage, if you want, and have to fish out these particular events massively, right, out of this whole thing. This is the challenge. This is exactly where technology, computing technology, comes into play, right? Okay, this is the data processing scheme. So we have physics, some interaction, creating these exotic particles. Of course, we have a detector. This is actually the Alice detector, but it doesn't matter. I like this one, this picture. And then, of course, what you do is you do feature extraction on front-end electronics. You extract, for instance, the energy from a certain sensor, or you determine the tracks of a tracking detector. You extract that information. You do online computing to also try to reconstruct the whole event topology. Right, that's what you want to do. And then hopefully, probably most likely you also need some distributed computing, because you cannot have the full resources here, but you also need to couple it to other facilities in the world. And then hopefully at some point you have a PhD student or a postdoc who is able, after all data analysis, to extract from particular spectra, if you want, some exotic features, some exotic particles, right? And you have a discovery. And of course this whole process, well, that takes of course years to somehow get to this particular point. So this is all computing. This is all computers, all data processing. So the data processing over the years has become more and more important. There's also more, of course, detector control, that's also data processing, and also data management. If you produce a lot of data and you have to keep track of it and manage it, well, you have to also spend a lot of time and effort to have also a nice data management system. Keeping also to the so-called FAIR principles, findable, accessible, interoperable, reusable, all these kind of things, right? So that is also a thing. And then on top of that, you also need a lot of Monte Carlo simulation. You also have to simulate, you have to make a simulation of your whole experiment. First of all, to design the experiment, to make sure that you have the right detectors at the right locations and whatever more to do your physics, right? That's what we are doing basically now in preparation, right? For that you have a model of your detector. A lot of computation time using Monte Carlo, but also during the analysis itself, you need some particular device which you use to optimize your analysis strategies, to use to get the efficiencies of the experiment, and so on and so forth. Right? So this is also a huge computational effort. Right? So the whole thing is only about computing, if you want, nowadays. Right? Okay, so let me just focus a little bit on these three items. This is me. In 1998, I did my PhD in the University of Groningen. We had also a little accelerator, a cyclotron, called Agor, actually a French device, doing quite nicely. Much lower energies, this is with protons up to about 200 MeV or so. So these are low energies. But at that time, things were different, right? We're talking about 1998. So let me show you how, roughly in one picture, how the data processing at that time went. So this is how it looks like, a typical experiment. The data acquisition was actually very simple. Was very simple. You had about in the order of 500 detectors. These were actually barium fluoride detectors. It was photon detectors. You measure the energy. We also have some wire chambers, getting some information out, right? And those information, well, you had discriminators, right? And those discriminators, the logic signals you used to build a trigger. And in those times, you were happy if you could make a coincidence between a couple of detectors. Maybe have some memory logic unit to do it a little bit smarter. But you had a simple kind of trigger on a LIMO cable. And that LIMO cable, then you connected to ADCs and TDCs to wake them up, to start integrating, charge integrating and stopping the time, whatever, of the signals which are coming. Right? And the signals you delayed. You need some time because the trigger made it was like 500 nanoseconds or so. So you need to delay it. So you put a lot of cables there, right? So that was all cables, pulling cables. This particular electronics, which was Cambridge and VME, you did not put close to the detector. No, you were scary. No. You put everything outside the experimental hall, right? Because you're afraid that during the beam you cannot just go in, right? So, but you still want to play with things, right? So but it all has changed. But this was the time when I did my PhD. And the nice thing is a PhD, I worked on all the facets of this experiment, building the setup, building the data acquisition, making the analysis scheme, and so on and so forth. But nowadays, the scales are completely different. That you cannot do anymore with 1 or 2 graduate students to set up the whole experiment. You need a whole collaboration, right? Okay, but that was the late 90s, right? Okay, the picture, reaction rate against event size. So this gives you somehow the data rates over the years from various experiments. LSC, by the way, this is the LSC experiment. This is run 1, so these are nowadays they also moved up here enormously. So I have to update at some point the spectrum. But here I was in 1998, 1 megabyte per second or so, typically the event rate. Peanuts nowadays, right? Then, okay, I got involved in BESS3, in the plus and minus collider in China. Okay, already moved up here, right? And then HADES, this is what we're doing here now, in the order of it can go up to 10 kilohertz or so, typically. And here we want to be in 2032, for instance, with the Panda experiment, right? So we're breaking, this is all log scale, right? Just look at this is all log scale what we're dealing with. So the whole processing becomes way more challenging, right? Over the years. Yes, and yeah, we cannot make use of, there is a Moore's law, absolutely, right? I mean, the number of transistors is also growing, double every year. But the clock frequency is basically, has stalled already when I did my PhD in 2000 or so, right? And already at that time, double core processors came out and, things are changing. There was a whole paradigm shift already taking place. But it also means that the software one has developed in the 90s has to be adapted, right? It was a whole paradigm shift in data processing as well, right? Okay, so what is nowadays the picture of how to analyze the data? And nowadays the buzzword is free streaming online data processing. You don't use a hardware trigger anymore. You cannot use a hardware trigger anymore. Your detectors, they produce data autonomously, producing in buffers as a front-end electronics, creating buffers. And then on different stages, some particular compute nodes where data is being collected, where some first level analysis is being done. You combine by data concentrators the data. And at some point, at some particular level, after already some pre-processing, you start making what we call event selection. You already almost reconstruct the whole event, what you normally in the past have done offline, you do now online. And then you start deciding, hey, wait a minute, this looks like a tetracore candidate. Let's keep this event, right? No trigger involved anymore. This is now the whole change what you do. So that means essentially that that online and offline computing are merging together, right? So this is another picture. So we have 10 megahertz interaction rate with Panda, right? And then we only will be able to store about 10,000 10 to the 4 events per second to make it all manageable. But it means that online we have to do all these kind of algorithms, track finding, feature extraction, vertex fitting, particle identification, kinematic reconstruction, all have to be done online in situ, right? This is the thing what we are essentially dealing with. So in other words, online and offline in the upcoming experiments will actually merge, which also means that there's a lot of pressure on doing online computing, right? Online, I mean, after all, I mean, now with offline computing, well, you can, you take some data with some simple trigger, and offline you can make a mistake and you rerun the data again. No, you might lose all your data if you don't do it properly during the experiment, right? So this is now really something which is coming online. Now, how do you tackle this thing? Well, there's a buzzword which you hear now constantly. It's called you have to federate. Federation, that's important. Of course, if you build a collaboration, then there's also federation. I think you also guys are all federating for this GNU radio, right? So federation is something which is extremely important. Also in our business, federation, hardware and software. Federation in on and offline computer. Federation in distributed computing. Federation in anything that has to do with computing, right? This is now the thing which one has to follow. Okay. Let's go to software design. I'm getting now closer to also your business here. A couple of cultural facts how software is being designed or being used in our communities, right? First of all, people like to see fast progress. So if you build a framework and you give it to your collaboration, they want to see very quick results. It might not be perfect result, but they want to see results, right? They're not going to wait for 1 or 2 years. So the learning curve should be actually the learning curve should be steep to be technically correct in wording. I think often people use it in the wrong way, but you have to get knowledge very fast, right? So that's the thing. Now this is something which I was actually computing coordinator in Panda for some time, and actually we killed the whole framework here, an old framework, because it didn't connect to this particular item here, right? There's no distinction between the users and developers. Developers are sometimes users, become, because they know a little bit how to program, they become a developer, right? They do something, right? This is somehow the thing we don't have really often people really dedicated. Yeah, there are always a small IT department here where they're dedicated, but in the collaborations, no, there are no, let's say, engineers, software engineers. Hardware engineers you find, but software engineers don't exist. Code is then also often developed by people who do their PhD or postdocs. And their PhD is about physics. If you come with a PhD there and say, I spent my 4 or 3 years on doing code design, you will not get your PhD degree. Now you can do it aside, but it's often then something difficult. But I think it's changing, by the way, but this is certainly something which we worry about. Yeah, and reinventing the wheel is unfortunately a very common practice. That is probably what you see in any kind of software world over there for some reasons. To be stubborn, I know it better how to do it, but sometimes also lacking information, right? And it's an evolutionary kind of process, right? So this is not, to build something by design and then deploy it and everyone is happy. No, you start with something and then you let the users play around with it. You get some feedback. Of course, you also need the whole communication system around it. And you progress in building your particular software framework, right? And lastly, in a certain point, is the recognition of software R&D still lags behind other R&D. So hardware R&D, that you can publish, that's a good part of your PhD, but software R&D, that's a side issue. Thank God it's changing. There's even nowadays a journal, which I'm actually one in the editorial board of that, Computing and Software and Big Science. So the recognition is getting there, right? But not yet fully, right? Okay, so what is important then in order to still be able to realize something? Well, the buzzword, of course, is frameworks. I think you're well also very familiar with that particular concept because, then you have also a controlled way that the whole user community is using the same thing. Productivity boost, accessibility, scalability, flexibility, blah, blah, blah. All these points, yes, you need a good framework. You need a good software framework. So I guess I don't have to explain that to you, right? Because you also deal with this. But the real question is always how to make a framework actually successful. How do you make sure that it's actually being used? How do you ensure that your collaboration actually is nicely and livid, and that the lifetime of your software is also holding for a very long time, right? That's of course the point. That's really what's making a framework work or not work, right? Okay, there's a good examples over there. This is root. I also understand today that GNU Radio is also making use of root functionalities, right? Now this is a framework already there since 1996. So again, when I was doing a PhD, I just moved from POR. That was more a Fortran-based kind of framework, also coming from CERN, by the way. And we move into this object-oriented thing, which was called Root. In my time, I didn't dare to touch it at that moment, but when I came a postdoc later, yes, it became a standard, right? That was a successor, the successor of POR, the Physics Analysis Workstation. And that is now has a huge community, right? It's very much concentrated on scientific data, storage, processing, visualization, analysis, statistical tools, very broad, also even now a machine learning tools there, an interactive interpreter, beautiful, people have done a low threshold to immediately do something with it. Huge community beyond the high energy physics community, right? If you look all the community, hadron physics, nuclear physics, heavy ion physics, particle physics, other communities making use of this particular framework. And of course also can run it on many kind of platforms, right? Okay, now based on Root, there's also a local success story. This is called Fair Root. This was from the IT department here. I see Florian over there is also part of the team maintaining and developing the so-called Fair Root kind of framework. This is a framework since 2003. This was more or less when, in this case, CBM, I think they started using this. They wanted to have a framework where they can do simulations, realistic Monte Carlo simulations to design their particular tech. That was the start of it, right? And they want to have something which immediately gives you very fast some results, right? Instead of that they have to somehow figure out how to use AR and how to do this and this. No, in that case, you know, the IT department here came with a nice framework, a modular kind of framework, of course making use of the root library functionality and also making use of all kinds of transport models to do this Monte Carlo simulation. At that moment, there was a Jean 3 transition to Jean 4. They do something smart. They use virtual Monte Carlo where you can easily switch from one model to the other, right? And then they also have a task kind of mechanism which allows then the users to easily set up their simulation framework and later on their analysis framework with all kinds of, you know, nice functionality. And this is now a very big success story. It's not only CBM is using this, but also Panda later used this, and R3B, these are nuclear physics experiment users, and also outside FAIR, people have started using these kind of successful frameworks. So that is a typical success story of what I call federated kind of computing. It even had some kind of spin-off. So Fair Root, also people at Alice, that's CERN. I'm now moving towards CERN now, Alice. Alice, by the way, also GSI is involved in the Alice experiments. There was already some kind of natural connection between the Alice community and the Fair community, but also on the software there was some kind of spin-off, some federated kind of spin-off going on. And there, for instance, Alice is already a running experiment, right? They're taking data, it's a heavy ion experiment. They look at lead-on-lead collisions at very high energies, much higher energy than at FAIR. They were running, right? And they already have a certain framework that's called the O2 framework. That's the online-offline framework. And they already, at that moment, start realizing, they're of course already way ahead in that sense because they have a running experiment, that you need somehow to merge the online and offline, couple it to your data acquisition system. And they were also actually at the stage to upgrade their detector to go to higher intensities. Just to give you some feeling about, you know, in 2021, they start preparing for run 3, which already have taken place, which produces, you know, data in the order of 3.5 terabytes per second, right? So these are huge, these are really large data streams, waterfalls of data. They have to do with this, right? They have to do with it. The reason was they upgraded their time projection chamber, which has to do with these particular higher rates. And at the same time, FAIR, that's here, we were preparing these experiments for CBM and Panda and NuStar and so on and so forth. We already also thought about this concurrency problems which we have to deal with, right? And of course we also like to see this merging of this online and offline. So that is of course in a natural kind of combination where also the both types of experiments, these are the 3 experiments, one at FAIR for the future, CBM, Panda, also with huge data range, and then with Alice, right? So the natural thing is trying to see whether we can combine our knowledge, and there came a new product, it's called Alpha. I guess it means Alice Fair, with a combined kind of framework to tackle these concurrency problems for data acquisition, to have this online data acquisition somehow being enabled. And the trick here, I will not go too much into detail, is that they actually developed a so-called FAIR message passing software framework, which is based upon a very old model. It's called the Actor model. This is already from 1973, right? Based on these simple kind of state machines, which gets a message, do something and pass a message or kill themselves or create something, right? I mean, so it's basically another kind of layer on top of your internet, which allows this message passing and which allows to build up in a scalable way a whole network of processes running in parallel, dealing with this concurrency issue, right? And the nice thing about it is fault tolerant. If one of these messages, if one of these devices here gets killed for whatever reason, it still survives, right? I mean, those kind of things are very important. And it's very scalable. It has, of course, a communication layer, something which is also familiar to you, 0MQ, dealing with shared memory, also being able to communicate over libfabric. So that's the product, and that actually gave successes. It gave successes. For instance, this is now the picture from Alice, where now there's a transport layer. This FairMQ, this alpha framework, has been installed on top of their data model and on top of their data processing layer. This is where the user sees things, right? And this is really hidden by the users. But at least it seems to work. They indeed have now a whole nice data acquisition system where they could merge the off and online kind of activities, getting this 3.5 terabytes per second of data being pre-processed using this kind of layer over there, 230, and then also offline using the same kind of algorithm, the same kind of system, doing a recalibration, eventually dealing to a permanent storage, right? So that seems to be very successful, but also the whole kind of framework is being used for CBM. CBM is not a running experiment, but we have a mini CBM where we have, a set of detectors, small set of detectors, which will also be used for a mini CBM, putting together in Beam. And also one of the things, of course, is testing the detectors and whatever more. But also an important element, actually the most important element, is to test this online data processing, using now also these FairMQ kind of bases, right? And that is also something which has turned out to be very successful, where you have under the triggerless front-end electronic kind of scheme, using now the first level event selection, also involving the green IT cube, the whole kind of line, the whole kind of event processing has now been demonstrated with such a mini CBM, also giving rise to even some particular physics peaks over there, which I will not go into detail. Okay, so that's one thing, right? Federation. Federation is an important kind of element. The other important element is go outside your box. Try to get your algorithms smarter, more efficient, and so on and so forth. So this is a thing which I personally was very much interested in, to see actually how we can actually improve our algorithms to get things a little bit smarter, and hopefully also deploy it to online computing. Right? So that is a thing which I thought of. And of course, what you have to do then is to look outside your boundary boxes and communicate with other kind of groups in the world, like for instance with astronomers, or like for instance people from computing vision, or people from biology, right, where they also develop algorithms, smart algorithms, and learn from them and see how we can also use it for our hadron physics or high energy physics kind of experiments, right? Now the topics over there, computing vision, machine learning and AI, they have of course becoming an enormous kind of boost, as you can imagine, over the past years. And this is also, I think, looks extremely promising. Okay, why do I think it's promising? Well, first of all, it has become very trendy. Extremely. This is, if you look up the word machine learning, artificial intelligence, deep learning, you do a search over there in Zenodo, for instance, and you try to get the number of articles which mention those kind of words over there, you will see that over the years, somewhere about 5 years ago, it games exploded. Right? Explode. Now you might think, yeah, maybe people have just published more. Well, also the fraction of those articles have exploded as well, right? So there seems to be something from the past 5 years which made this very interesting. And this is certainly not my articles here, right? This is the community, different one from physics, from chemistry, material science. There's a whole kind of community is now seeing how they can use, and that machine learning and AI becomes more and more important to do their kind of research, right? So it seems to be a boost going on, right? Now the question is there some wave again, like we have in the 90s, right? There was also some particular wave on this. Well, that's still the question, but certainly over the past 5 years, it has been boosted up, right? Another boost here, AI. There's also we are living in the state of Hesia, and there are all kinds of universities. They also get funding from the state, and they put things together, and the topic AI, right? And they also now are trying to lobby, big lobby groups, trying to get funding on this particular thing. And also here, GSI is involved, we rent out part of our green IT cube to build an innovation lab, AI innovation lab, right? So there's also here certainly a new trend going on, and we are also somehow involved, right? Also on the German level, this is on the state level. On the German level as well, well, digitization in Germany is also a word nowadays. It's, well, if you realize that people in Germany are still using fax machines, I guess it's not a big surprise that they worry about digitization, right? But also here in Germany, there's a big lobby towards German funding agencies called BMBF, trying to get funding for computing-related aspects, where AI and machine learning becomes also an important element. There's a whole kind of consortium being created, a bottom-up consortium. They organize all kinds of schools and workshops to train the trainers, but also to train young researchers to learn about deep learning, to learn about the basic concept, and so on and so forth. So this is a whole kind of thing which you now see over the past 5 years boosting up. And also towards the EU, the European funding agencies. We also have to there trigger and see what we can release over there. And there's also a new consortium being built up. It's called the EU CAF. This is actually fundamental AI for fundamental kind of physics, which recently has started to, they had actually an opening workshop in Amsterdam. And that is also meant to get interest to AI from the various communities, including nuclear physics, and lobby this to the EU, right? So there's a lot of trendy things going on from the publication point of view, from also the lobbying kind of view related to machine learning and AI. So what is really going on here in the past five years? Well, first of all, if you look at AI, and you look at perceptron, the concept of a perceptron, right now I'm talking about deep learning over there, is already from 1943. Right? So the mathematical idea of representing, let's say here, a piece of brain there, right, as a perceptron in a mathematical way, it's from 1943. So that's quite a long time ago, right? So this is, in that sense, nothing new, right? What is really new is, of course, the big tech people coming with large language models, right? Transformers has become extremely important, right? And they are also very successful. I mean, just this is over the past 5 years. You see here ChatGPT-4, right, with the order of 117 trillion of parameters, typically, right? And that has been grown exponentially. It has been grown exponentially, and nowadays have these very powerful machines. And that all happens roughly about 5 years ago. And this is somehow also picking up from the scientific communities. Right? This is the reason why the things are being boosted. Now let me put it somehow into a certain concept. Let me take this particular picture where I show you the number of parameters of these language models, right, these transformers over the years, and I'll put it with respective to the number of synapses in brains of mammals over the years. This is actually the so-called Schwarz plot, showing now the evolution of mammals over the years. Right, so here we have the mouse. It's also divided into a different thing. We have a cat, chimpanzee, and there we have our humans. The number of synapses is in the order of 150 trillion. ChatGPT, 170 trillion. The growth, look at the growth. The growth here, this is red line. This is what nature does, what evolution does, if you want, right? The growth in AI is this blue line over there. It goes at 10 to the, both are growing exponentially, yes, but the AI is growing actually with a factor 10 to the 6 larger than that. Now you might think, okay, maybe the software in our brains is way more smarter at the moment than I could be, but the question is, will that change, right? So certainly it is clear that also humans will have to also use AI to get more information out and rely on what they get and to trust them, right? That's the whole thing what you have. And people might also say, yeah, but you know, humans might also get smarter, you know, this is maybe a little bit overdone. Well, think about a cat, right? The cat is over there, about 70 trillion synapses or so. You will never be able to learn a cat how to do chess, right? So there is a limit. Also, humans has a certain limit. But in principle, AI, or at least the blue line over there, in principle has no limit, right? So this is something to think about. I think this is, for me, it really dawned into me that one also has to realize where this particular boost comes from. And of course, one can also then get scared and all these kind of things. But this is a reality. AI will help us, and AI will actually be able to provide information which we are not able to do or get. And they have to dumb it down for us in order to understand it. This is how the reality will look like in the future, at least if you trust these kind of particular pictures, right? Okay, now of course getting a little bit into basics. Machine learning applications, right? I mean, what are we doing now? I mean, machine learning is also something which is not very new, right? We're all using it. If I ask, for instance, a student which comes and say, look, I mean, do you know machine learning? Or he or she says, no, I never use machine learning. Well, then I say, yeah, but hang on. Did you ever fit a spectrum, like a least chi-square fit or whatever from data? It says, yes, well, you did machine learning. Ah, that's machine learning, right? Using algorithms to get knowledge out of data. That's a fit. It's machine learning. Of course, this is a simple one-dimensional kind of thing. If you want, of course, we can go to much more interesting feature spaces. Clearly, right? This is now what we're doing, but we're trusting this already, right? Classification, for instance, right? Classification. If you want to do tracking, doing half transformations, or doing Riemann filters, or doing all kinds of things. Yeah, we are certainly trusting the result at some point, right? Or think about clustering. That's certainly some very common theme if you look at clusters of an electromagnetic calorimeter. Yeah, there are algorithms that do it very smartly and very efficiently, like for instance a mean shift or based on some neighboring kind of relations. Or fitting. Now we nowadays do very fitting on complex data, having kind of physics constraints to improve resolutions and all these kind of things. It's very common. If you write this in an article, nobody will argue for these things anymore. If you use your analysis, a boosted decision tree to do classification signal background. 10 years ago, people were not trusted, but nowadays, no issue. You can do these kind of things. People believe what you're doing, right? Now the question is, can we go one step further, right? Can we actually go to the next level? And this is now where people are thinking out at the moment, the promise for the future. Detector responses, we're using these Monte Carlo simulations, using these tracking, these are very computationally expensive things, right? But nowadays you also have gun networks which can produce images for you. Why not try to use those kind of things to model the detector response? It's way more efficient. You can save a lot of computational time. Assist in detector design. We have complex detectors, millions of parameters and sensors. And we like to design an experiment optimize a certain physics. This is an optimization problem in very high dimensions. Something where you can use AI for, right, or machine learning. Real-time event selection. Anomaly detection, data mining, experiment operations, all these kind of things will over the years become more and more important in our particular field. Even the word foundation models is nowadays falling, although I still don't really understand what it is, but it doesn't matter. There is all kinds of new things coming here online. And is it all hype? Well, of course, I always say, well, as long as you keep this particular rule, is don't use a cannon to kill a fly, I think this is fine. Right? Okay, let me give you two examples, and then I also close up here. First of all, now you see already a self-driving car here, right? That's very clear. Now you might also, I always thought, okay, I mean, self-driving cars, that is also something which will come at some point. Of course, there's all kinds of resistance because people also like to drive themselves. But then I also thought, yeah, wait a minute, if you have an experiment which is very complex, why not consider also a self-driving experiment in the very long run? What is wrong with this? Actually, I think you need this. Look at these detectors. They are very complex, right? Look at the fact that that in the future, in the near future, we will have beams at extremely high range on the very harsh environment. These are heavy ion beams. There's a lot of radiation going on, right? So stability is becoming very important. We want to do this in situ event reconstruction. So we have to make sure that our calibrations are correct, always correct. Nowadays, we can do, in the old experiment, you could do the calibration offline, right? And you update your data and whatever more. But now you have to do all these things during data taking. Okay, so maybe one has to rethink the whole business here. Cost, right? I mean, it's very high. I mean, this beam time is very expensive. Human resources are very expensive. If your detector system in your experiment becomes more and more complex, well, you don't get more beam time, right? You don't get more people. Forget about this, right? So you have to do something smarter. And of course, if you have a PhD and a postdoc, you need also to publish. They have to finish their project in 3 years. If you have a complex detectors and you have this PhD student spending 3 or 4 years to calibrate the data, you can do it now. The complexity is small, so now they have to spend half a year to a year on calibration. But with such a detector in such an environment, it will not work anymore, right? So these things, I think, are underestimated in the experiment. Accelerator people already understood this. They already understood, to make stable beams, you need some AI there. That is there, but experiments are lacking way behind here. Okay, let me give you some feeling for this. And I go to an experiment which we are running these days. It's called the Hades experiment at Fair Phase 0. So when I moved from Groningen to Germany, 1 month later I was involved in this experiment. There was an experiment in 2022, yes, 2022. Proton runs, some hadron physics experiment. I was really enthusiastic. Yes, we have to do it. Now this is an interesting detector. It's a detector which is, it's somehow in between the past and in the future, right? It's already a very complex detector. It already has quite a lot of sensors, if you want. It's also complicated, many types of sensors. It also has a data acquisition, which is still trigger-based. There's still a physical trigger, right? But still, the number of detectors, their front-end electronics is already getting very smart to a certain extent. And also the event rates, typically up to 20 kilohertz with 400 megabytes per second. These are reasonable large numbers. So it's getting to a certain limit where things already, you're stretching it already, right? Now to give you a feeling that we're stretching it, so this is a picture of a beam time in 2022. This shows you here the operation, the shift. You had two, we have to be in the counting room. This was, by the way, during COVID time, so you see people had a mask here. So we couldn't have more than 2 people in the room, was not allowed. But of course you see always, this was at night on Sunday or whatever, right? You see always like 2 or 3 or 4 people in the counting room. And then also online, there were about 10 or 20 more, all monitoring the individual detectors. Looking at spectra, if something wrong, call the people on shift. And the people on the shift don't know what to do, data acquisition crashes, call somebody else, this and that, right? There was a big operation going on in order to get things running. Now this is still doable. This is still something doable on this scale. But now imagine, you have a CBM experiment where the rates go up by orders of magnitude. Complexity goes up by orders of magnitude. This will be a killing fact. You have to do something smarter on this level, right? You cannot rely fully on the human resources to do all these kind of things, right? So this becomes really a panic situation. This will be somebody on shift, right? So I hope then that, one also can have some rest as a human, right? And hopefully then also have, let's say, an AI kind of system where you essentially, conceptually plug in the environmental variables, the beam parameters, the beam settings, the beam conditions, maybe even some Monte Carlo data. So you have also a model of your detector in there, right? And then, hopefully during the experiment, pushes out calibration constants of your detector on the fly, right? On the fly. And even if you're really daring, be able to change actually the high voltage and settings of your experiments. Let the system do it, right? Now, if you show this to people at Hades, they think, no, we will not do it. So this is certainly a conservative kind of theme behind it. But I think this is really needed also for the future. Okay, now of course we have some pilot experiments. So this is actually a graduate student of mine who's at the moment in Warsaw at the Hades meeting. There's a Hades meeting going on. And he already started looking into AI or machine learning, some neural networks, some convolution kind of neural networks, to see whether one can do these kind of things, right? So what he did is he take the data from 2022, rewind it back, right? Picked one particular detector. In this case, the drift chambers, so they are used for tracking particles, right? You bend the particle in magnetic field, you get the tracks of that, and you get the momentum out. But these things are also being used to do particle identification. You measure the energy losses. By time over threshold of pulses, you measure the energy losses. But, the gas is a gas system, so you're very sensitive to environmental variables, right? So your energy loss, it's called the EDX, will change over time, not because of physics, but because of pressure in the gas and so on and so forth, right? Now the question is, can we somehow build a system which spits out these calibration constants online? Of course, we didn't do it for a running experiment. We replayed back an old experiment, but see whether we can do it, right? And it seems to be very successful. He uses a long short-term memory network and a graph embedded in the graph convolutional network. And indeed, he showed that this is essentially the EDX over time. So this is a nominal value, and then because of calibration changes, it starts fluctuating because of mostly of these environmental. This is basically the main feature factor which is relevant. And here, this is the training, and this is, for instance, the red with respect to blue. Blue is the target. This is what it really is, if you want, and the red one is essentially what the system predicts over time. So yes, in principle, very smooth, you can do this kind of thing. Let me give you another example. And for that example, this is my last example, I go to Japan with you. This is our colleagues in Japan, also have an accelerator. It's called the Japan Proton Accelerator Research Complex. Somewhere over there, not so far away from Tokyo. They are colleagues. If you go outside GSI, you probably can see it also from here. You see this kind of little thing which pointing where other facilities are. This is where it is, about 9,000 kilometers away, JPAC. This is one of our colleagues, right? So also our friends there, also doing experiments here. We have a collaboration between each other, right? But they have also an interesting experiment. And one of the experiments what they're using, this is Taka Saito. He's working half-time if you want at GSI and half-time also in Japan. He is crazy about hypernuclei. So trying to discover nuclei where you replace the nucleons by a hyperon, so strangeness in there, so exotic nuclear matter. On the third chart, right, I showed you in the beginning, right? So how can you detect those kind of things? Right? There are only 5 events have been seen on the double hypernuclei, and he wants to see many more of them. Now he has a setup for that, and he uses a technique which is already from 1905. I think Rutherford used it, and that is called nuclear emulsion. These are emulsion plates. What he has a kaon beam, hits some particular target, and there are particular particles called cascades or so. They actually interact with emulsion plates. These are photographic plates. So they do an experiment, have a series of emulsion plates. They shoot a beam for some time on it, right? They stop the beam, they take the emulsion plates out, and these are photographic plates, and they develop it and look at images, right? So what happens if you go with a charged particle through these material over there, you have silver halide crystals, and they actually start getting bigger. And if you develop it, then you can see that very nicely. This is how it looks like. It's like bubble chambers, right? More or less, sort of, right? But this is now with photographic plates. Now the nice thing is that you have an excellent position resolution. It's better than a micrometer. So there's no other way with tracking the texture which we have here. These drift chambers and TPCs, you will not get such a high precision as given here. Right? So that is certainly one thing. So here you see, for instance, all these tracks. You see little dots. These are the beam punching through, right? But you see also these little stripes here. And these little stripes here come from a decay of something. And of course, what you're looking for is a decay of this exotic hypernuclei, right? This is what you're trying to do, right? But you have to analyze these images. So what you do is you take these many emulsion plates out. You build a microscope, right, and you make images, and you do some algorithms to try to find patterns in your data which might look to the event what you're looking for, right? This is the idea. Now these experiments are already pretty modern. They run for a long time. And if you use now the standard techniques, the standard algorithm, and the standard way of actually also where humans often has to actually look at things and check things, it will take about 560 years to analyze the data what they took. They took about 100 petabytes of images generated from these emulsion kind of plates, right? 560 years, well, that you can forget about. If you ask a funding agency to get a delivery result after 570 years, they will say crazy, right? So you have to do something else, right? And he, of course, came with the idea, yeah, why not using, in this case, mask CNN, so convolutional neural networks, using mask R, so these are region-selected CNN kind of things in masking, to get faster events out. And that turns out to be very nicely. He also used a GAN network to produce simulated data, which actually looks like real data. And it turns out, indeed, he can identify certain patterns. This is alpha part, these are calibration parameters. But indeed, it turns out it works very nicely. And he can actually calculate it. He can reduce from 560 years to 3 years kind of analysis. Now it becomes doable. Now people start happy. But you need to go to smarter kind of algorithms, right? Otherwise, you will not be able to do it. Okay, let me round up here. So, pushing the boundaries, femtoscale research with large-scale tech, that was somehow the title. Let me give you somehow the takeaways. Well, and hopefully then we can also have maybe a discussion about how we can connect with radio, GNU Radio. So, a couple of takeaways. First of all, evolution of femtoscale research fundamentally depends on breakthroughs in computational technology. Computational things are becoming essential. And the developments over there are also becoming essential to be able to deal with the next generation of experiment. There's absolutely no doubt about. And I think this also has been very strongly being recognized. Now, most of our computing innovations actually are already based on stuff which were invented, concepts. Well, think about the Turing machine from 1938. This is actually the concept that you guys are also using, right? So all these concepts, actor models, Turing machines, all these things were already invented decades ago. But now we start using it massively in a kind of interesting environment. This is really what you see over. This is very interesting, right? Now, as I said, online computing has become smarter, online has become offline. This is a thing that we are now tackling somehow. And as I said, the application of machine learning, or AI, but also I didn't talk about open science, so one can also think about the ChatGPT for the data which you produce over there, for data management. That also has attracted a lot of attention over the past decade, so the past 5 years, right? That's really what you see, right? Unfortunately, okay, one thing is the interest is mostly driven by funding opportunities and by excitement, technological kind of excitement, right? And I have to say, this is more a critical item, it's academic values. So the impact on scientific advances are yet underestimated by a large community, I have to say, but I'm sure it will be increasingly being recognized over the years. So that is something I think, I personally believe is the case. Okay. GNU Radio. Right, I started, well, first of all, GNU Radio, the integration and accelerator and ring activities at GSIFA, I think this is already there, right? I mean, this is beautiful. You have really a nice kind of collaboration, and you see some synergies, and you see the beautiful, right? There's no doubt about it. The question is, now large experiments, the thing that I present, are there things useful, maybe from both sides, where we can think about it? Do I have to believe the recommendation of ChatGPT? Question mark, right? To what level? What about the role of machine learning and AI? I don't know. Suggestions. So here I stop. I thank you, and I hope we can somehow have some discussion on these particular questions.
Thanks, first of all, for the great talk. When you showed the reduction of time from 560 years to 3 years in that example, how long and how did you do the training of the neural network?
Yeah, so the training is done on Monte Carlo. Actually, of course, you also will generate a lot of Monte Carlo data, right? So you have also model of the reaction of the emulsion plates is being modeled. That is then actually being pushed to, well, first of all, I didn't do it, but this is of course in Japan. Use a gen, that is actually training using a gen kind of network, which then can create on the fly very fast images which are as realistic as possible as training. So that is being done by a GAN kind of network kind of environments. So also there, deep learning is being used, not only to classify, do the inferences if you want, right, of the images, but also for the production of the image data. Monte Carlo simulations, producing something, you build a GAN network, then eventually making the pictures constantly, right? So that's the theme that is being used. The bottom line here, there's still 3 years, but you still have to do all kinds of mechanical activities, right? Still putting it, so that is that's really somehow, there's always a limiting factor, right? So there you have to realize.
You were mentioning the framework aspect of using things that others can then build on and think. And this kind of ties into it, because when I see someone having learned something, especially when they apply like GAN techniques, right? They will get what they asked for in the data, right? I ask my system to find the data that describes the statistical model, I assume, and if I then find exactly that, then in the classical system that would be kind of like result picking, right? I'm not doing an experiment to verify an hypothesis, but I do an experiment to find something that serves as hypothesis, and then I will find, yes, I can verify that because I just picked enough data to find something. So how does a large scientific group ensure that this does not happen? How do we ensure that when we're building models, be it like very classical, like I sit down with radio, I write a signal processing flow graph. How do I verify that my model of reality matches what I wanted to do? Or how do I verify that a complex model that I did not even design myself matches reality?
Yeah. Now, of course, you can also use the data itself, right? I mean, of course, there are a lot of, let's say, processes in these reactions which are pretty well known. So the modeling of this is very close. But of course, if you try to look something exotic, right, you don't want to explicitly put it into your frame, you know, because you need to know it, right? But it's about the things which you know you have to filter out. The things which you have to know has to be modeled properly. Anything else on top of that is essentially an anomaly, right? Yeah. So it's basically you try to filter out the things which you know. This is actually the concept.